the question there is like so. It says that you have a line, and the line is given in parametric form. You have a line, and you're given a point, B. The question says find the distance from the point to the line. Given the tools and the machinery we developed so far, this question is very simple. It can be very simply solved with all of the things we have. So I have this picture here, just to give you some understanding what's happening. Here's my point, B, that's the line. So if I call this L, that's my line L. I put here the vector, so if this is my vector A and this is the vector C, so here the vectors, so this is the A which goes to some position, to some point on the line. This is the C vector, which is the direction vector of my line. I also call the B, little b, the vector, the position vector of the point B. So it's this vector which goes from the origin to the point B, this long one. Now, if I want to find the distance, what I have to do, remember last time we discussed this quite extensively. We discussed this as a byproduct of the other thing, of the Cauchy-Schwarz inequality. And remember what we did? We built a special function which sort of depends on the parameter, and depending on that parameter, it computes the distance from the point B to an arbitrary point on my line. So we built a function which measured the distance from B to an arbitrary point, and then with the help of the analysis, well, it wasn't really analysis involved there, but still, we sort of minimized that function. We minimized that function, we found this special point, the distinguished point, which realizes this minimum. And we even gave a name to this minimum this second. We have to take this blue vector, which originates from here, all the way to the point B, and we have to project this vector on my line. By doing so, we will find this special point where my minimum of a distance will happen. And that explains the recipe or the algorithm which I will follow in a second. I will take this vector, which goes from this point, from the tip of the vector A to the point B, and I will, just with the formula which we have now analytical formula for that, I'll project this vector onto my line, and I will find this little red vector, which will be the projection. I will call this vector U when I find it. And then the distance which is asked for in the question on page 16, will be the length of a difference between the blue vector and the U vector. Look at this. What I'm saying is this: if my U vector is the projection of B take A, that's the blue one, B take A is a blue vector, and U then be this little red one, the projection, then the distance we're after is this length. It's the length of B take A, the blue vector, subtract the projection which we'll find in a second. So you don't have to do this minimization all the time. All you have to do, you have to remember the analytical formula for the projection and the geometric purpose of the projection, geometric explanation what the projection is. I gave you this dashed line just to bring this up in your memory again, how we found this, but for the purpose of this exercise, we don't need to do that. We don't need to do this minimization. As long as we remember the formula for the projection, the formula how to find this little red vector, we're done. Let's just do that. Here's the formula for the projection. We have to take the C vector, the vector onto which we project, the one which sits here in the subscript. We have to dot product this vector with the one we actually projecting. On this occasion, it's a difference, B take A. We have to divide by the square of the length of that and multiply by C. That's the formula for the for the U vector. That's the formula for the way we find the projection. If you don't remember this formula, you have to revisit like a few pages back in this notes. All we have to do now, we have to follow this. If I follow this, look what happens. This is the length of C vector. That's the C vector. So the length of that is sum of the squares of the components. 1, 1, and 4, which happens to be 19, so 18. So root 18. This is the length which I will put in here. In fact, because there is a square here, there will be just 18 with no square root. Dot product, that's a dot product of a difference. I'll open it and I'll take it through you. I'll take you through it. The left factors here, 1, -1, and 4. These are the components of the C vector, right? 1, -1, and 4. That's true. The brackets here, that's the B take A vector. 0 take 1. This 0 take this 1. 3 take 2 is this 3, take this 2, and A take 3 is the last component in the B vector, take the last component in the A vector. I think I did the arithmetic here. You can double check me if you don't believe me. I think it should be 18, right? Negative 1 here, another negative 1 here, and here 5 times 4, it's 20. 20 take 2, it's 18, yes. So we now can say what the distance will be, because all we have to do, we have to sub in our values. By 18, this value will go into the numerator here. This 18 will go into the denominator, which happens to be just 1 after you take the fraction. This is just a coincidence, just to make the arithmetic simpler. In some other questions, you might have some real fractions involved. And then I have to times it with the C vector, but because this is U, my U actually just C vector. My U is actually just C. Of course, this picture now is lying, right? Because if this picture was up to this vectors, this U must be should go all the way up to all the way to the end of the C vector. But this is a general picture. In general, U may be shorter or longer, or even in the other direction. This also might happen if C was, for instance, going this way. Your projection still will be U this way. So this is just a coincidence that in this particular question, U ended up to be just C vector. So my distance, which is like this, I have to replace this U with C. So my distance is like so. Let's just see if I'm correct. B take A. Maybe I just put here some. No, I didn't put anywhere. I didn't put anywhere explicitly what B take A is. But remember these brackets. These are the components of B take A. So B take A and take another U will be negative 1 take another 1, it's negative 2, that's why it's negative 2 square. Here we have 1 and take another negative 1, that's why we have another 2's here. And here we have 5, which we subtract 4 from this 5, so it's 1. 2 square plus 2 square plus 1 square, it's 9, root of that is 3. So the distance is 3. As simple as that. Again, all of this geometric machinery, it is sitting under this projection formula. All of this preparatory work we done like last week, now it pays off. We don't have to think much about it. We just take the projection, knowing the meaning of that projection, and the rest is just a pure computation.